Morning, everyone. Oh, good. Good to hear. We have a project due tomorrow. We have an assignment due next week. And beyond that, we're just having fun in here, whatever that means to us. We were in the process last time of talking about different Turing machine models. We ended up talking about countable and uncountable infinite sets. And we ended up talking about how there were quite a few countable infinite sets, and sometimes you just had to be clever with how you think about ordering the infinite set, and it became countable, when in other ways it was not so countable. So it's countable if and only if there is one such algorithm that can enumerate all of the strings in that language in some order such that for any given string in the language, you will eventually get there. We ended up with this example, and we found that for this example, there were ways to order this such that it was not countable, but there was a way to order this such that it was countable. So the set is countable since there is a way to order it and enumerate it. Any questions before we dive into the next fun bit of content? We'll go do it. The next thing we're going to talk about is an interesting limitation to automata, a linear bounded automata that is a Turing machine that has an interesting limitation. So a couple of days ago, we talked about all of the different interesting ways to extend the power of a Turing machine. Didn't really extend the power, I shouldn't say that. It allowed us to represent it in a different way that looked more powerful, but in fact represented the same language. But are there interesting ways that we could limit it? Are there ways that we could to do that? So if we do this, then we could find that with certain restrictions, we could allow for and find some additional efficiency inside of this idea. So we can think of an NPDA as just a non-deterministic Turing machine where the tape is restricted to be interacted with like a stack. That is one such interesting limitation of a Turing machine, and we can find that we can emulate the idea of PDA with it like that. But are there others? If we limited access to a finite portion of the tape, to just say we don't have an infinite amount of tape, we have exactly 100 cells, or we have some limited amount of tape space, then we could define a finite state machine based off of them. But here's an interesting question. What if we limited the tape to only the amount of space that the input occupies? So as the input scales in size, we allow ourselves more tape space, but just as much as the input occupies. So there's still not a finite bound on the size of the input, but we can't use more tape than the input, which means that we need to store information if we're going to modify parts of the tape. The question is, does this limit the languages that a Turing machine can accept? And if so, does it limit it in an interesting way that has value to us as computer scientists? So to do this, we would have special symbols, kind of like bookmarks or bookends is the better way to do this. That is a left bookend and a right bookend that says we can't go past either of these bookends. And between that, utilizing every single cell is the input. We can't rewrite these end markers. They're read-only. Read-write head cannot move left or right from either of those bookends. And we can assume non-determinism here because it's equivalent. Just like with other Turing machines, we can show that it's equivalent if we allow for multiple tracks. where each one is bounded to the same size as the first track. So there's nothing here that says that you don't have access to more memory than that, but it's again bounded by a constant times the size of the input. So let's give you an example, because it's fun. Let's see if we can find a linear bounded automata accepting the language a to the n factorial. And you don't have to draw out the states and transitions. I'm more interested here in just an intuitive idea of what is the algorithm that you would produce to be able to do this when you're only limited by the amount of space that is the input. So to use 5 factorial, there'd be 120 a's on the tape. We want to determine yes or no. Is that an even factorial? Think about that for a minute, and if you get any good ideas, let me know. We can share them with the class.
What does linear bounded again mean?
It means that it's bounded in space by the size of the input.
Okay.
So yeah, if there are 120 A's on the tape, we have 120 cells. You can take a second track that also has 120 cells, but you don't get any space on the left or right of those 120 cells. There are 140 A's on the tape. We have exactly those 140 cells to determine that is not a factorial.
Do we have an infinite number of tracks?
You can have a finite number that you dedicate at the start. So in this case, a second tape might help you, but beyond a second tape, we don't need more than that. Any ideas for how we might do this? So if what's on the tape is some factorial, at least some factorial that's larger than 1 factorial, is it divisible by 2? Yes. What happens if we check if it's divisible by 2? How could we check for that? Yeah,
Could you switch between the state that goes like even odd, until you get to a blank? And then-
yeah. So what we're gonna wanna do is on the second tape, put 2 of something. And then you're gonna pass left and right and left and right and left and right through that. And whenever you reach a blank on the far side of that, so you're basically going to not delete, delete, not delete, delete, not delete, delete. Something that alternates between those two in a way that tells you that when you're at the end of something, then you should delete. So your 2 there is going to help you to do that. The remainder, once you delete half of the values from there, is that remainder going to be divisible by 3? If it's a factorial. Should be. Something like the definition of 5 factorial is 5 times 2 times 3 times 2 times 1. And multiplication is all commutative, so it doesn't matter the order in which you do that. So you could go 2 times 3 times 4 times 5 to get there. So any factorial is going to be evenly divisible by some number, and what will remain on the tape at the end of that is a single A. When you divide 120 by 2, you get 60. By 3, you get 20. By 4, you get 5. By 5, you get 1. There's a single A left on the tape at the end of that. So the process is going to be start with 2 of something on the second tape, delete half of the numbers, then add a third, delete when you reach the end, reset, delete when you reach the end, delete when you reach the end, reset, delete when you reach the end, etc. Check if there's a single A left on the tape. If not, add a fourth, then go through that same process. And if at any point you find yourself with nothing left on the tape, the first tape, then it wasn't divisible. And you're good. Or you reach the end before you reach the end of you reach like a 1, 2, 3, 4. I'm at the end when I'm trying to get the 5. That would say that it's not divisible by 5. And it should be divisible by every successive number until there's a single A left on the tape. Does that make sense to people as an algorithm?
So first we delete every second. Then do we delete every third or?
Yeah.
Okay, and then every fourth.
Yeah.
If there's 4 factorial.
Yeah. So by delete, I don't mean replace by a blank, because then we'd never know when we're done. We want to replace it by some seen character, kind of like we have before. So a small factorial, 2 times 3 is 6. We could do something like, all we have here are A, with our left bookend and our right bookend. Then on our second tape, that is also bounded to be exactly this, we're going to place, it doesn't matter what we place here. It could be a 1 and a 1, doesn't matter. But again, we have our left and our right. And the idea is that this is a blank. We can move to the end of this, see this blank, and then move until we see the left bookend. When we see the left bookend, we know that we are done. And we can reset to this CC, delete. CC, do nothing and delete. So this would say, we are here, we start on the blank, we move over and do nothing. We move over and move over here. We move here and see this L, which says delete this. We're going to turn this A into something that we've seen before. Reset this whole process. Then as we move here, we're going to move there. As we move here, we're going to move there. As we move here, we're going to see that we're at the end, so we should delete where we currently are. Reset, do exactly the same thing. That's going to delete here. So now we have half of the A's removed. Reset all the way to the left here. Reset all the way to the left here. Actually, all the way to the right here. We're going to add a 1 here to now we're deleting every 3. So now we're going to move, recognize we're at the end and delete. Move, recognize we're at the end and delete. So if we would move, recognize we're at the end and delete. So in this case, well, sorry, we want to delete and move at the end and keep. Sorry, so we would X, X, recognize we're not, leave it here, recognize there's a single A left on the tape, and decide that it's factorial. Again, this would be disgusting to actually write the transitions out. But as it stands right now, that would work. Where the idea is you successively divide by the next larger number. Divide by 2, divide by 3, divide by 4. And if at any point at the end of one of those phases, there's a single A left on the tape, you know it's divisible, it's a factorial. If at any point it's not, where you're in the middle of trying to move and you reach the end and you're not at a point where you want to keep that A, then it's not a factorial. So yeah. So we use that second tape to keep track of the current divisor. Lots of transitions. But now the question that I would have for you is, are linear bounded automata more or less or equally powerful compared to NPDAs? If we had access to a stack, could we emulate this? If we had access, basically, can this emulate anything that could be emulated with a stack within a linear bounded automata? And could it do more than what an NPDA could? Or could it do less than an NPDA could? Any thoughts on that? I'm going to start with equal. Who thinks they are equally powerful to NPDAs? Few people? Less powerful than NPDAs? More powerful than NPDAs? Hard to know, isn't it? But the answer, I like querying people's intuition on these because I find that more often than not, general intuition when it comes to abstract thinking is frequently wrong. But the right intuition here is they are in fact more powerful than NPDAs, which is interesting, very interesting. So we could show that this language is not context-free by the pumping lemma. In fact, you did this on your homework. So because this is not context-free and is accepted, that's just part of a proof. But we could also show that we could emulate a stack within this. I mean, we kind of, a couple slides ago, talked about how you can restrict the operations of the tape to work like a stack. How about, the real question is less or not less powerful than unbounded Turing machines? What do we think? Do we have the ability to do everything that we could do with an unbounded Turing machine with a linear bounded automata? Or are unbounded Turing machines more powerful in some sense? Let's say, let's start with equal again. Who thinks that linear bounded automata are equally powerful to unbounded Turing machines? Who thinks they are less powerful than unbounded Turing machines? Most of the class has it. They are less powerful. If they were equally powerful and with a limited amount of RAM, we could do whatever we could do with infinite RAM, as long as we had enough RAM to represent the input. And that is not something we can do. That's my intuitive takeaway from that proof, but a much more rigorous proof is in the book. And as always, I highly recommend going through and looking at that process. If I introduce an intuitive idea to you as to why that would be the case, try to go read the mathy version of that and try to tie that intuitive idea into that math, and the math will start to make a lot more sense in a way that trains you to read that math. All right. Done with slide deck 16. Our slide deck 17 is going to talk us through the idea of how all of these language classes that we've talked about, and even some that we haven't talked about, are related. So we talked about defining classes of languages, but only some of those have some kind of reasonable meaning. There are an infinite number of classes of languages, but a lot of the differences in classes of languages don't do much for us theoretically or practically. So which ones do, the ones we've talked about, and why are they important? What other ones haven't we talked about that are reasonable? So one of those classifications is the languages that a Turing machine can operate on. We have not talked about that exact class or defined or had a name for it yet. But there's another one we're going to talk about that if we thought that context-free grammars were as powerful as grammars could get, boy, do we have another thing coming. All restrictions from grammars are going to be removed as we talk about another class of languages. So let's talk about two new classes of languages. The first we're going to call recursively enumerable. A recursively enumerable language says that there exists a Turing machine that accepts it. What we mean by accepts here is that if the string is in the language, then a Turing machine will halt in a finite amount of time with a yes answer, that this string is in that language. However, rejection is not defined. If a string is not in a recursively enumerable language, then there is no guarantee that a Turing machine can halt in a finite amount of time. It may go into an infinite loop. It may just take a very long time to reject it, which means that we have no idea and cannot tell between the ideas of it will eventually reject or it can never tell us. So this is a class of language that exists outside of the scope of what a Turing machine can decide, if we're going to use the idea of deciding, meaning answering both yes and no for a particular string. I should say yes or no, whichever one it is. Yeah.
Is there automaton or a class of automaton that can accept or reject one of these?
There is not. This is outside the scope of what we can say yes and no to. We can say yes, but we make no guarantee about whether we can say no. There will be some strings that aren't in the language where we can say no, and there will be some strings in the language where we can't say no in a finite amount of time. And nothing that we've talked about with a Turing machine and nothing that we have discovered at all in theoretical computer science can answer no for all strings in this class of language. So we allow the Turing machine to go into an infinite loop and never halt. That's going to be a built-in part of a recursively enumerable language. If the answer is no, it is okay if we construct a Turing machine that says no by never terminating. So for all strings in the language, Turing machine will accept it in the finite number of transitions. For all strings not in the language, Turing machine may halt and reject it, or may enter an infinite loop. So that is recursively enumerable. And we'll talk a lot more in detail about how to do something like this here in a minute. But the second class of language we're going to talk about is a recursive language. And a language is recursive if we can build a Turing machine that can say yes or no to every possible string. So this is the class of language that directly maps to what a Turing machine can do, when it can answer yes if the string is in the language and no if the string is not in the language, both in a finite number of steps. We'll talk about what it means for there to be a membership algorithm, but a membership algorithm will exist for every recursive language, and that is not the case for recursively enumerable languages. So a membership algorithm just means that we can go through an algorithmic process that looks at the entirety of all strings in the star closure of the alphabet and can separate them into those that are in the language and those that are not in the language. That process won't terminate because there are an infinite number of those strings, but we're not going to get stuck on anything. You can imagine trying to do this on a recursively enumerable language, and if the Turing machine goes into an infinite loop, there's no way for us to know that it's gone into an infinite loop. So it's ambiguous between whether the Turing machine is going to halt and reject at some point, or whether it will never do so. Just because it's been running for 10,000 years doesn't mean that it's stuck in an infinite loop and will never terminate. Maybe it will terminate sometime in the next year. We don't know. So looking at these definitions, are recursively enumerable languages recursive? Basically, which is a subset of the other? I see some shaking of heads. That is correct. Why?
Because the recursively enumerable ones go into an infinite loop to signify that they are not accepting it, basically.
Yeah, basically, we would have to be able to build a membership algorithm to be able to do that, and we can't do that. Are recursive languages recursively enumerable? They are. This is because we allow both for rejection in a finite amount of time and going into an infinite loop. It's just that recursive languages all reject in a finite amount of time. So when you allow for this or that, and this entire class of languages does this, then it's a subset of this or that. All right, one thing we're very much interested in computer science is enumerating these kinds of languages. So we want to construct an enumeration procedure, construct an enumeration algorithm. So if we have a class of language that we can answer both yes and no to in a finite amount of time, then how could we go about dividing those strings into the yeses and the nos? Any thoughts on that? What we have here are Turing machines. What we want to do is construct a Turing machine that is able to, if we successively feed it different strings, it can answer yes or no to those strings. But we also need a way to generate those strings. So what we're going to do is we'll design a Turing machine that we'll call Turing TM membership. That is going to determine membership in the language. We feed it a string, and it's going to be able to answer yes or no, whether that string is in the query recursive language. This is very similar to what we've done so far with some languages in class and on the current homework. Then we need a second Turing machine. We'll call it TM generator. That is going to basically take the star closure of the language, and it's going to start making in some concrete order that will get to any particular query string, all of the strings in the star closure of the alphabet. And as it does this, as it generates a new string, it will feed that new string into TM membership, which will then decide yes or no, is it a member of the language? And between these two Turing machines acting in tandem, we can have an algorithm or a process for dividing these strings into in the language, not in the language. And there is no way that this process can't make progress, because we can answer yes or no in a finite amount of time. So TM generator writes its output onto TM membership's tape. As we generate new strings, we're going to write those strings on the tape. And then TM membership is going to follow along behind, answering yes or no to every one of those strings. TM membership writes onto an output track only those strings it accepts, and we end up with all of the strings in the recursive language. Again, this process never terminates because there are an infinite number of strings in the language, but we can define a process that enumerates those strings. There's no string in the language that this process wouldn't get to at some point, if given an infinite amount of time. Does that concept make sense?
So is TM membership just writing these strings, each one immediately right after another on the output track?
Yeah, so the generator, we basically have, let's imagine that we have generator and we have the membership. The generator is going to be going through, and if we had ABC star, it would come up with the empty string, then A, then B, then C, then AA, then AB, and AC, and it's going to be writing each of those onto the membership's tape. So it's going to be going along here, writing every possible string in the star closure in some order, and the membership will be following behind and determining to the empty string, yes or no, to A, yes or no, to B, yes or no. And there's a second tape here for membership, and the membership is going to be writing along here all strings that are in the language. So maybe lambda is not in the language, but A is. Then we're going to have an A followed by some kind of separator character. Who knows what that is? We'll call it $. Then maybe B is in the language. Separator, $. C is not in the language, but AA is in the language. So we would have AA as the next string, followed by some separator. And this process would continue on forever. And what we would have here are all strings. And here we would have all strings in the language. So if a string is on this tape, then it's in the language. If a string is not on this tape, then it's not in the language. And so we have Turing machines that just go through this process paired together, two different processes running at the same time. And at the end of that process, there is no end, but the idea is for any string that is in this language, it would eventually get written to this tape after some finite amount of time. You give me a string, I tell you how long this process takes to write that string on this tape if it's in the language. So it is a complete process, even though it never finishes. It's defined in such a way that it's not skipping over anything. It's not getting stuck in a loop that means that it can't finish. At least with the current thing that it's working on. We'll never finish the whole process. Questions on that? Okay. That was the easy one. Recursively enumerable languages, we want to do the same thing. How in the world could we possibly come up with a process that writes every string that is in a recursively enumerable language on some track of a Turing machine? Remember that for a recursively enumerable language, if there's a string that's not in the language, our poor Turing machine may go into an infinite loop. If it goes into an infinite loop on a particular string, does it get to the next string? No. So we need some more intelligent way of doing this. Very much like ordering strings in order to be able to come up with an enumeration procedure. For that, we had the example yesterday of trying to write strings in alphabetical order. And we found that that didn't work. There is something that works here that allows us to do this. Can anyone think of it? So if we're going to answer yes, we'll answer yes in a finite amount of time, which is great. We need to be able to do that, to be able to write what is yes on the tape. Yeah,
Could we come up with a way to have like an expected number of procedures? And then if you go over that for a certain string of some length, then you would be out of it.
that would be nice, but it would require us to limit the language class that we accept. So there would always be some language for which that doesn't work. That is a very good idea. So have some way of saying, if it's going to fail, it will fail within this many steps. Unfortunately, in the general case, we cannot make that claim. Very good thought.
We have some kind of Turing machine that acts as a sort of stopper for the working Turing machine, and if it's determined that the string is not in the language, that it writes some kind of stop character to the tape.
So how that would be great for the strings for which we can determine it's not in the language. But at some point, it's going to be ambiguous. We're 10,000 steps into this process. Is it going to terminate or not? That's the point that we need to focus on. Because we can't determine, yes, it's going to halt. Because we don't know. It's ambiguous whether it will or it won't. That's the real challenge. Good idea. It's okay. I don't expect a classroom of computer scientists to come up with this, because this was a very big deal at the time that it was invented. So yeah.
So usually before we said that a Turing machine would halt whenever it goes to the infinite loop, right?
Well, it hasn't, by definition, it hasn't halted. It halts whenever it can answer yes or no. But if it's in the middle of an infinite loop, then there's no way for it to halt.
Are there, for every Turing machine that has an infinite loop, is there an equivalent Turing machine that halts rather than loops?
That is a great question that we're actually going to answer in about the next week or so. But the answer to that question ends up being no. There's no way for us to determine that. Which, if there were, that would be a great path to go down. The answer to this question is that for everything that we have yet to accept, we have to define a finite number of steps that we're going to allow it to go before we stop and move on to the next one and say, you know what, we're going to come back to this later. And very much like in the rational numbers table, we were working diagonally down that table. We're going to set up a table that looks at every possible string in the star closure. So these columns go on forever, W4, W5, etc. And we're going to look at, this is the first move that the Turing machine makes, second move, third move, etc. At some point, some of these are going to finish and either accept or reject. Some of these are going to be stuck in infinite loops. But the idea is, if it gets stuck in an infinite loop, we don't want to continue with that thread forever. We're going to make some progress on that thread and then stop and move on to the next one. Then eventually, we come back to it and continue from where we left off. Makes a finite number more moves, then move back to the next one. And we'll skip over any of these processes that have terminated with acceptance or rejection. But the basic idea is that for every thread that will accept, it will still accept it in a finite number of loops. Some of these threads we will continue to come back to and make more moves on and just continue to loop and loop and loop and loop, but we're not stuck there. We're able to pause it, move to the next thing, come back to it later. Does this table make sense to people as to what's going on? Here are our strings. This would be our lambda, our A, our B, our C, our AA, our AB. And we would set up the Turing machine to be able to answer, is lambda in the language? And in some number of steps, we may be able to answer, yes, lambda is in this language. The empty string is accepted. It may be that in some number of steps, we can say, no, lambda is not in the language. It may be that the Turing machine goes into an infinite loop trying to answer that question. but we were going to simulate just the first move of that. We're going to set everything up to answer this question, and then we're going to make one move on this Turing machine. Since this tape and the Turing machine is infinite, we can just save this process, put a separator character that says, all right, for this, we're going to now move past this, write a separator character, write the next string past that. We're going to simulate the first move on this second string, on A, and if it accepts or rejects on that first move, great, we have an answer. If it doesn't, the next thing we're going to do is to go back to lambda and simulate its second move. We're going to restore the state of lambda after its first move and simulate the second move. Then we're going to set up B. We're going to simulate the first move on B. If that doesn't accept or reject, we're going to move back to and restore the first move of A and simulate the second move of A. Maybe that accepts at this point, and we know that A is the language if there are just two moves, in which case this entire rest of this is going to go away. Whenever we would come back to this later, we're just going to skip over it. Question?
Are we gonna have to code this for a project?
No. I do not hate you that much. This is very complicated, and there's a ton of setup and manipulation to this. This is not, the idea here is it theoretically possible to do? And the answer is yes, it is theoretically possible to do. But yeah, it's complicated. A lot of theoretical computer science is just asking the question, if we hated ourselves enough, could we do this? But the important thing here is just understanding how and why this works. If we could set up such a process like this, we could come up with a membership algorithm for a recursively enumerable language. At the end of this, for every one of these strings that is in the language, eventually we would have reached a point where it simulates enough moves to be able to accept it. When it accepts it, we can write it on a membership Turing machine's tape, and every single string that is in the language would eventually get written to that tape. Or rather, there would be no string in the language that would not be written to that tape eventually. Again, that process never terminates. But the process would write forever strings in this language to the tape.
If a string is accepted in fewer than a certain number of states, would it continue to go to that point, or would
Nope.
it just?
We basically we're gonna eliminate it from the list to go back to. We keep track of a list of currently running strings, and then we would be iterating them from back to front,
So
one move at a time.
that's not the list of all strings, that's just the list of active strings.
Yeah,
Okay, got it.
yeah. So when we determine that either yes or no, we've terminated and accepted or rejected, we're gonna remove it from that. Or if it's still there, skip over it. Have some way of saying, have some flag that says currently in operation or not currently in operation. To either skip over it or not. Yeah, it's fun, it's cool. It's really complicated, and I would never make you do it.
It's one of those things that's more fun to think about theoretically than it is to try to implement.
Oh yeah, that's a lot of computer science, at least for me. That's why I became a professor and I'm not in industry actually implementing things, because I like thinking about things more than I like doing them. All right, so this is two classes of languages that we have found. Recursive, Turing machine can say yes to or no to. Recursively enumerable, Turing machines can say yes to, but maybe not no to. Then there are some languages that are not recursively enumerable. And I keep spoiling the very first question on my slide, but thinking beyond the scope of what is recursively enumerable, are there languages that are not recursively enumerable? What would it mean for a language to not be recursively enumerable? How could things get worse than that? We actually talked about an example of one of these yesterday. Was there a language that we talked about where we could not necessarily say yes that a string was in the language?
Is this the one with the prime numbers?
It's the real numbers, yeah. So being able to say, imagine coming up with, or attempting to come up with a membership algorithm for the reals between 0 and 1. We saw with Cantor's diagonalization proof that it was not possible to even list them all in any kind of order. So how could we hope to come up with a membership algorithm that you give me a real number, and I can guarantee that in some amount of time, this algorithm produces that real number? Cantor's diagonalization proof says that we can't do that. So by that, we can tell that real numbers between a lower bound and upper bound are not recursively enumerable, because we can't even answer yes for sure. So recursively enumerable says we can answer yes, but we might not be able to answer no. Not recursively enumerable says we might not be able to answer yes. So we talked a bit about why we can't enumerate this, but here's another interesting one. Assume that we have an infinite countable set. The one that I like to use here is binary. Binary is an infinite countable set. We agree? It basically maps to the base 10 positive integers. And there are a few that are equivalent. You can have a bunch of leading zeros on a number, but we can now make an infinite countable set where we say, let's iterate all binary numbers of length 1, of length 2, of length 3. Okay, I'm done writing these. The idea is this goes on forever, but it's enumerable and it's countable. So now the question I have is the power set of that set countable? And remember that the power set is just all possible sets of any number of combinations of those numbers. So we would have the set that contains none of these. We would add to that the set that contains one of these, the set that contains 2 of these, 3 of these, 4 of these, etc. But since they're an infinite number, is there a way to enumerate all of that? And a way to add these different sets to a set that is the power set? The answer to this is no. There's no way to do that. Spend a little bit of time to try to convince yourself of that, or think about how would we try to do that. You could try to dimensionalize it, where we're going to add some set of size 1, some set of size 2, some set of size 3. There are an infinite number of these in an infinite number of directions. So there's no limit to how you could do that in a way that makes sense. And in fact, you can set this up exactly like Cantor's diagonalization proof. For real numbers, you just say, assume that there was a way to iterate all binary numbers, so that here's the first binary number, the second binary number, etc. And we would have some number that goes on forever. Who knows? And we would have an infinite number of these to generate the next number, some number that is not in this infinite list of numbers that go on forever, that this goes on forever. You just say, we're going to create the nth number, proving that it's not in this table by taking the first digit in the first place and inverting it, the second digit in the second place and inverting it, etc., down the diagonal. And since there's always an inversion of the existing digit, you just flip that bit and you generate a number that is not in this table. Even this process wouldn't produce infinitely long binary numbers. But you can assume that an infinitely long binary number, these are all infinitely long, if they terminate, then it's the equivalent of throwing a bunch of zeros in front of it, making it infinite. And it works out. So the power set of an infinitely countable set is not countable, which is a strange result, but one that's pretty powerful. So just a couple of examples of non-recursively enumerable languages. So exactly the same thing. What's fun with this is that this result leads us to be able to conclude that there are more languages than there are possible Turing machines. And that's really strange too. So if there are more languages than possible Turing machines, then by definition, there must be some languages that aren't possible to construct with a Turing machine. And those languages are the languages that are not recursively enumerable. So we're out of time, but we'll come back to this. We're getting closer and closer to what's going to be a fun video day in here.
Video?
Yeah, we're gonna watch a video for a class period at some point. It's still a couple of class periods out, but we're getting there.
You're freaking about.
Because it's
Drop to it and everything.
Office hours starting now for anyone who wants any help.
Yeah, no, fair.